All right, thanks again. So as Ben mentioned, I'll be talking about multi-thousand channel ecog grids today. And like most of us here, we're all interested in potentially mapping the whole brain and with cellular resolution if possible. And across all the modalities that we all use, we face more or less similar technological challenges. Now, these technological challenges are multidimensional, but I'd like to depict them with three-dimensional diagram that we see right here. First, we'd like to have large numbers of sensors to afford us the data that we need. We like to do these measurements at high spatial resolution and attain as much as possible large brain coverage. So ideally, we would want to be at the tip of this green arrow right here. However, traditionally, especially in electrophysiological systems, we were limited by the number of channels, and to be able to attain large brain coverage, we had to sacrifice the resolution. This has been the case for many decades in clinical electrodes, where we had a few tens of channels covering about 60 centimeters squared or so from the surface of the human brain. And with advances in microelectrode technologies and thin film microfabrication, we're able to stack a large number of electrodes generally in a small area and do microelectrode recordings from the surface of the brain. And over the last decade or so, we're able to push this thin film technology to thousands of channels distributed over broader surface coverage, as we will discuss today. And these are the two pillars that I'll be talking about from our laboratory at UCSD. So briefly, what are these fundamental technological challenges? If we want to stack a large number of contacts to measure the brain activity, we would like to scale down the electrodes. Planar electrodes have a low number of absorption sites to have electrochemical interactions with the brain, and therefore random processes become very effective at small dimensions. And this shows in the noise of these electrodes. Here we're looking at the noise as a function of frequency for different diameters, and as the diameter scales from 1 millimeter to 20 microns, the 1 over F noise scales as 1 over D squared. Now, if we go to volumetric sensing materials like polymers, or if we go to roughened surfaces where we have both sharp tips, sharp corners that facile the electrochemical interactions, and also a large surface area, the number of absorption sites increases, random processes have less of an effect, and then the 1 over F noise is plateaued at the amplifier noise for all of the microelectrode diameters. Now, the electrode size has also implications on the amplitude of the signals, not only the noise. Here we're showing this for 3 contact materials placed within 50 microns from each other, P dot and 1 order of magnitude higher platinum, and then another order of magnitude higher titanium. This is in terms of impedance. And as we get to the titanium electrode, the measured potentials to the same evoked activity, the amplitude is reduced by about 10% or so. This is because the impedance of the electrode becomes a fraction of the input impedance of the amplifier. This also has implications on the time at which we record the signal, the time delay. So relative to P dot, as the impedance increases by 1 and then 2 orders of magnitude, we can have a fraction of a millisecond delay in the recording of the same activity. So as much as we would like to have real-time neural recording, even at the level of the microelectrode, we're really in near real time. Second fundamental challenge is connectorization, and we're leveraging advances in microelectronics industry and wireless transmission in order to have parallel data transmission. And the third one is to be able to adhere to the curvilinear surface of the brain and have a stable contact interface with the surface of the brain. So this is what a clinical grid looks like during intraoperative mapping, but now with the thin film electrodes, one is able to conform to that curvilinear surface. And if we add the thin film manufacturing capability, we can stack large number of sensors and wire with thousands of traces in order to extract data from those sensors. So the devices that we will talk about today are platinum nanorod grids. This is a scanning electron microscope image of how such a grid looks like. It has perfusion holes. The overall thickness is about 6 microns, and the contact diameter is 30 micrometers. And recessed below the surface is a mesh of nanorods that are about 50 nanometers in diameter, 500 nanometer in length. This is so that if the electrode moves on the surface of the brain, the rods wouldn't rub against the tissue. So we classify the use of these electrodes from a clinical perspective, similar to the FDA classifications. Acute, less than 24 hours. This is primarily used in mapping eloquent and diseased tissue for surgical decisions. Semi-chronic or subchronic, this is used chiefly for monitoring in the epilepsy monitoring unit up to 30 days. And then chronic, this is mostly for neuromodulation purposes, where one would want to have stimulation and possibly recording to close the loop in this intervention.
Quick question.
Yeah.
Are these subdural or they go over the dural?
These are subdural, and I'll show more moving forward. All right, so we'll talk about 3 topics. First, we'll talk about a grid that will show a panoramic view of the neurodynamics of the brain activity with microscale resolution. We refer to it as a brain telescope. We'll show it in the context of 3 human experiments in the intraoperative domain. And then I'll briefly talk about displaying the brain activity directly from the surgical field with the brain IEG microdisplay. And then in the last few minutes, I'll talk about an end-to-end wireless epilepsy monitoring system. So here again, these are subdural electrodes. These are the clinical electrodes that are used typically in surgical interventions. They're built on thick substrates, and therefore they're not conformal to the surface of the brain, have poor spatial resolution. Additionally, the surgeon sits on one side of the room, the electrophysiological team on the other side, and they communicate verbally, creating an efficient link of information exchange between what's happening in electrophysiology and how to relate this information to the surgical decisions. So we wanted to simplify this process, and as I go through the slides, you will see how some of the technologies that we are developing apply in this context. Now here we're looking at a 1024 channel grid placed on the surface of the human brain during a neurosurgical procedure. You can see the contacts very well. You can see the metal traces to these contacts, and these are the boundaries of the grid. This is 3.2 by 3.2 centimeters squared. It's about 6 microns thick, so it's highly conformal to the curvature of the brain. It's also compliant to the brain motion, and this allows us to have a mechanical lock or stability between the contacts and the cortical surface, and therefore attain stable and high-fidelity recordings. Now, we've used this in the operating room of Dr. Aslan at OHSU, and the first procedure that's done is to define where we are at the surface of the brain once the skull is open. This is usually done in a procedure called central sulcus mapping or motor mapping, where an electrical pulse is applied to the peripheral nerve, and it evokes somatosensory evoked potentials. Once the phase of the somatosensory evoked potential changes from first negative to first positive, we know that there's a transition between motor to sensory regions. Now, this is typically anatomically marked with the central sulcus, where you have a blood vessel. But in the case of lesions in the brain, there is reorganization, and the only way to know where that boundary is through functional mapping, the procedure that we just described. Applying the platinum nanorod grid, we were able to observe the curvilinear nature of this functional boundary and show that it is indeed curvilinear at a millimeter scale. Now, with the clinical approach, usually a lot of linear interpolation is done, and we'll not talk about the surgical implications of that, but we'll talk a little bit about some of the behavioral experiments that will fit into this context. So first, we put vibrotactile simulators on the fingertips and evoked activity across each one of them. And this stimulation evoked activity in the somatosensory cortex below the functional boundary that we have identified from the first experiment. In certain cases, the patients are awake, so we mount hardware to monitor their behavior, for instance, hand movements, and time lock this behavior to recordings that we attain from the surface of the brain. So this is rendering of the activity on the reconstructed MRI image of the same patient during a hand grasping motion. The arrows are the spatial derivative of the phase, and in the background, the green dots are the potentials. In 2D, again, the background are the potentials, and then the arrows are showing the direction of the propagation of the waves back and forth between the motor and sensory region during the hand grasp. Now, this is expected, but has never been seen before with the resolution that's afforded with the grids here. Now, tumors often induce epileptic discharges. Here we're looking at interictal discharges with black dots, and the contours are potentials associated with these discharges. So with this millimeter scale resolution, we're able to track where the epileptic discharges start, the nodes of epilepsy, and how it propagates across the surface of the brain, with the potential of delivering treatment to the epileptic nodes focally, either by resection or by delivery of stimulation. Now, in another configuration where patients are listening to auditory stimuli, we placed a high-resolution grid with 200 micron pitch on the superior temporal gyrus, and we have a randomized trial from Eric Hallgren's lab where different phonemes and noise are induced, and across these trials, across different patients, we observed responsive regions or modules. These are cortical domains or functional units that are associated with each individual English phoneme. Now, the diameter of these modules is on average about 1.8 millimeters, with a transition of about 0.4 millimeters between two adjacent domains. Therefore, if we want to resolve these domains with high gamma activity, as shown here, or with ripples, we'd need a resolution of at least 1 millimeter contacts that are at most about 100 micrometers in diameter or so. Now, where is this all going in terms of channel counts? A few years ago, we started a collaboration with Cash Lab and Hallgren Lab with a few hundred channels. In 2019, we started our first recordings in humans with 1024 channels. And today we are working on 4,096 channels with large animal experiments already underway. We are at a stage similar to 2018 where we figured out how to do the connectorization for these large channel counts. So within 2 years or so, we expect, if we get funding, to be able to do a 100,000 channel recording system intraoperatively, and then 2 years after, deploy it in the semi-chronic setting. Now, as we learned how to analyze this data online, and we wanted to project this activity directly in the surgical field to inform the surgical decisions, so we collaborated with the Cash Lab to implement light-emitting diodes on the surface of the grids. This is based on gallium nitride micro-LEDs, wafer scale process with in a multi-project wafer architecture. The entire device is about 25 microns in thickness, mostly made with flexible films. This is a cross-section of a scanning electron microscope of an individual LED. And the idea is to take the brain recordings and with the laminated LED on top, projected directly from the surgical field. On one side of the grid, we have the microelectrode arrays, and we have metallization to provide the ohmic contacts to the LEDs and to act as a mirror to project light from the other side. So to test this, we performed a control experiment in our lab. Last year, we've published a paper in which we've shown that with high gamma mapping from the whisker barrel cortex, if we excite individual whiskers with air puffs, we can resolve their individual cortical columns. And we validated that with post-mortem histology with one-to-one agreement between the functional map and the anatomical map. And then we placed the LED array, and then we started exciting one whisker at a time, and we've shown that the location of the light projection varies with the whisker that we stimulate. If we induce an epileptic drug, if we apply an epileptic drug, we can see the epileptoform in real time propagating through the array. Now, the goal of this is to provide maps that will inform the surgical decisions. So on top, we're looking at the functional boundary. This is the motor mapping that we discussed earlier, projected in a green light, and then the epileptic discharges are projected with a red light. Or functional maps for limbs, for instance. These are regions that the surgeon needs to protect, and then the pathological activity relative to that functional unit is projected with red LEDs. Now, this is all in the intraoperative setting. To move toward the subchronic or semi-chronic setting, and in the future toward chronic applications, we want to eliminate the wiring that comes out of the head. This is to reduce the burden of wires on the patient, reduce the risks of infection, and at the same time leverage the high resolution that's attained in our lab. We're working on two systems. First, an ecog system. This is the subcutaneous unit part of the system. We have a grid with 1 millimeter pitch contacts distributed over 6.4 by 6.4 centimeters squared for recording, and 256 channels for stimulation. We have acquisition and data streaming electronics in the subcutaneous unit, and then antennas for uplink, downlink, and power delivery. This will be implanted in a similar way to the responsive neurostimulation system, the RNS system, in epilepsy patients. And mating with the subcutaneous unit is a lightweight head-worn unit that will have an antennas, a power amplifier, and a single wire to a belt, cell phone-like battery plus Wi-Fi data transmission. For depth electrodes, we have a similar architecture. We're developing a frame in which head stages will clamp into the frame, and then we have a low-profile head-worn unit for data streaming, and again, a single wire that will go to a belt-worn system which has the battery and the Wi-Fi data transmission. We built some of these systems. This is a version that has been tested in large animals. And this is the version that's more compact, that's out in manufacturing as of this week. This is for the depth electrodes, so this is the setup shown in the pig operating room, and we validated the operation compared to a control which is wired. We have similar fidelity in the recording, similar baseline, and similar power of the recorded signals. Now I'll talk for 2 minutes about the depth electrode and try to conclude very quickly here. So. Traditionally, to map activity or stimulate from deep brain structures, depth electrodes, such as the one that you see here, are about 1 millimeter in diameter, have up to 16 contacts. And these are about 6 millimeters spaced, about 3 millimeters in length, either platinum or stainless steel. And so leveraging, again, the thin film microfabrication techniques, and to use a clinically compatible approach, we developed inflatable depth electrodes where one can insert a stylet to inflate the electrode to implant it, and then the stylet can be extracted afterwards. This has a similar length as an reach, about 8 centimeters or so deep into the brain. And these are optical microscope images of how these electrodes look like. Here are the platinum nanorod contacts. The stainless steel stylet is shown below, and this is the back of the electrode. The benefits of this are numerous. One is that the lesion that it will create is very small. Two, it's very flexible, so one would be able to attain more stable recordings and hopefully be able to carry out these recordings and stimulation for longer durations of time. The electrodes afford clinical monitoring and stimulation with about 16 macro contacts and then 128 channel microelectrode contacts that could be distributed across the whole shaft. We've used those across species, including in humans, and here we're showing one example in the cash lab where we've recorded single unit activity in HPs in the acute setting. Now, to interface with this, we're developing our own software. So there's, on the head-worn unit, there's a lot of FPGA programming. On the off-person computer, we're developing a user-based C++ library for data streaming and control, and we're working with colleagues at the Allen Institute for using OpenEFIS under a GMP setting so that we can deploy this to the epilepsy monitoring unit. The interface is user-friendly or clinical-friendly, where we could see grid-like activity. We could see, of course, traces and waveforms, and then we can select individual channels or groups of channels and in real time update the waveforms that we are seeing right here. Now, the goal is perhaps obvious to most of people who we have here. In general, one bed in the epilepsy monitoring unit services one patient over a duration of about 10 to 14 days, and in some cases up to 30 days. But as we transition toward wireless monitoring, one can truly perform ambulatory digital monitoring, where one bed would service more than 10 patients in 10 days. So this would, of course, reduce the cost, increase the affordability, and make these procedures available to a wider patient population. So here I'd like to remind you of the things that we've seen today. We've talked about the brain telescope. This is a subdural cortical grid with large channel counts. We've done recordings in humans with 2,048 channels, and soon enough, in the winter of 2024, we'll do it with 4,096. We've demonstrated a brain IAG microdisplay, and we're making headways in our epilepsy monitoring unit, hopefully with an FDA approval within 1 to 1.5 years to start our clinical trial. Now, the work is done with many fantastic colleagues at 3 institutions, UCSD, OHSU, and MGH, primarily the Sid Cash Lab, Eric Hallgren Lab, and Anamad Raslan. These are the mentees who have helped in generating the results that I've shown here today, and we're very grateful for the Brain Initiative funding and for UCSD's funding. So thank you for your attention.
Hello? Hello? All right. Thank you so much, Dr. Dayeh. I think we have time for one question.
Yes.
I can probably just show. I actually have 2 small questions for you. With the gains that you're seeing in terms of your channel counts, is that more due to the size of the film expanding and your ability to transmit that information, or is it due to the density of the electrode contacts increasing on your film?
Both of them, and the main challenge is really connectorization and learning how to do connectorization to each of the contacts on the widely distributed contacts.
Makes a lot of sense. My second quick question is, in terms of foreign body response, like, you know, as you expand the size of this subdural implant, like, morbidity is going to go up. Like, how does the tissue respond to this, and how chronic do you really think this is?
Yeah. So we don't have chronic data yet on this device from large animals or humans, but we know it's thin profile, so it's very likely going to induce less of a tissue response. We know from clinical trials that use the cortical grids, some people have been implanted over 7 years with those grids, and they still function very well. So we think this would be better. Now, there are companies and academic labs trying to implant those in a minimally invasive way so that the skull opening would be smaller, and therefore it would be less of an invasive procedure from that perspective. Of course.
Okay, thank you so much.
Thank you.